So today's topic is solid principles, right? So there are mainly 5 solid principles, right? So SOLID. So these 5 solid principles are there. So basically there are 5 key object oriented design principles that help software developers create code that is maintainable, scalable, testable, understandable and flexible, right? So basically our solid principle will help to achieve these goals, right? So these principles were popularized by Robert C. Martin, Uncle Bob, right? And are widely used in the OOP design, clean architecture and design patterns, right? So what does solid stand for? Now S stand for single responsibility principle. Okay, that means a class should have exactly one reason to change, right? So that means in one class we will be having one feature. Okay, one feature. Okay, so that means it should have a one reason to change, to modify, right? So that means we will be having one feature in one class. Okay, second one is open and close principle. We already done this part in the previous lectures. Open for extension, right? Open for extension, close for modification. So if there is any class is there, we will not modify this, right? We will extend this. We will make the child classes. Okay, so this is what open and modification. Open to extension, close to modification, close, right? So third is Liskov substitution principle. That is, derived class must be substitutable for the base class. Means if we are using parent object, then we can use child object at that place. Okay, so this should be possible. This is what Liskov substitution principle says. So we will cover this part in the we can say detail further with the code, right? So third one is, that is I stands for interface segregation principle. That says client shouldn't be forced to implement unused interfaces. Okay, let's say there is one interface, okay, which is having 2 methods. Let's say one method is run, one method is jump. Okay, jump. Now there is one class for, let's say, a child that can run, but that is not possible to jump for a child, correct? So child will not implement this interface. Okay, that's what this principle says. The client should not be forced to implement unused interface. Okay, so it will not implement this interface. It will have some separate interface. We will see in the further example. The last, that is D, that is called dependency inversion principle. That is what? Depend on the abstraction, not the concrete implementation. That is what? Tight coupling. We should not depend on the tight coupling. We should use the loose coupling. Okay, we will see the example. So what is the single responsibility principle? It says a class should have a one reason to change. That means I'm saying one class will have the one feature. So that is called single responsibility principle. So it will be having one reason to change. That is one feature, right? The second one is open and close principle. We already seen this. That is open to extension, close to modification. If we want to add new feature, we will extend this class. Let's say child classes, right? But do not modify this. This applies to the interfaces also. Liskov substitution principle. This says the derived classes must be substitutable for the base classes. That means if we are using the parent object somewhere, we can use the child object also. That means there should be all methods of this parent in the child. Okay, so if some method in the child is not applicable for the parent, then it is not possible. We will see this example further, right? So just look for the definitions now. Next one is interface segregation. That means clients should not be forced to implement unused interface. That is this one. If there is an interface with run and the jump extract methods, right? So if there is a class child and we are implementing this interface and this child cannot jump, right? So we will not implement this interface. We will be having different interface for that, right? So the child should not be forced to implement the unused interface. Last one is dependency inversion principle. That means depend on the abstraction, not the concrete implementation. What means this tight coupling should not be there, loose coupling should be there. We should use this loose coupling. So the first principle is single responsibility principle. That says a class should have only one reason to change, right? So we can also say each class should be responsible for the one part of the functionality, right? Got it? So one class, one functionality. Okay, so let's take the real life scenario. A chef cooks the food, right? A server or waiter serves it. So don't ask a waiter to cook or chef to serve, right? So each class, that means each person is responsible for each functionality, right? Each principle. So let's take the code example that is violating this principle, SRP, single responsibility principle. This is the class invoice, right? What we are doing in this, first thing we are doing, what we are calculating total, right? The second thing is we are doing print invoice, and third thing is save to DB. So we are performing three functions here. That is not the principle, right? It's violating the principle. We should have only one principle, only one responsibility in one class, right? So that in the future, if we want to modify, we can simply modify the class. Okay, so this class does three things, that is business logic, output and persistence. Three reasons to change. We are having three reasons to change it. Got it? So if we apply the principle SRP, then what is happening? We are having different class for invoice. Okay, that is calculating total. The second thing is print. We are printing the invoice. Okay, invoice. Third part is saving the invoice, right? Saving to DB. So now we are having different class for different reason. Okay, now each class has only one reason to change, one responsibility, and where to apply, where the services doing too many unrelated tasks, right? So we should have one task assigned to one class, controller loaded with the UI, DB and the business logic, right? So we should have the different classes and the packages for all of these. And what is the benefit? Easier to maintain, of course, test and extend, right? We can extend it, right? And encourage cleaner modular design. Of course, one change doesn't break the unrelated things. Let's say we are making one change in one class, one responsibility, that will not make the change or affect other classes, other responsibilities. Okay, great. So these are some related design patterns: separation of the concerns, facade, single responsibility principles. Okay, we will check them further in the next upcoming sessions. So now the second principle is open and close principle. The definition is software entities, classes, modules and functions should be open for the extension but close for the modification, right? So open for what? Extension, and close for modification, right? So this is the principle. Simple. Open to extension, close for modification. If there is any class, we should not modify it. If there is a function that we need to add it, we can implement a new class. So you should be able to add new behavior without changing the existing code, right? This is the OCP principle. Let's take the real world scenario. A mobile phone let you add the apps, right, without changing it operating system code. So you can add the app, right? You will be having some different functionality for that. The additional, right, let's say additional class for the new app, you are not changing the operating system code. Got it? You are just adding it, or we can say extending your OS code. Got it? Let's take the example now. Here we are violating the OCP principle. What we are doing? We are having this class, right, notification service, and what we are doing? We are sending to the notification to the email and the SMS, right? We are sending notification via email and via SMS, right? So this is happening under the same class and under the same function, right? Now if we want to add new type, let's say WhatsApp, what we will do? We need to modify this class only, right? We need to change this function, add new functionality for WhatsApp. That should not be the case, right? That is not the principle. It's violating the principle. We should not modify, no, extension, okay, right? So how we can achieve this open and close principle? Using polymorphism, right? So we will be having this interface notification in which we are having this method send, right? This method is there. So we are making the interface of this notification. After that, for email we are having different class, for SMS we are having different class, and if we want to add the WhatsApp, now we can add the WhatsApp class also, right? Class WhatsApp notification, notify, and that will be implementing this interface, right? Implement interface, that is notification, and this we will be having the logic. Let's say send notification, and there will be the inputs, the parameters, right? The notification and the message, string message. Okay, so like this we can add the new class. Okay, so earlier we are having this email, this SMS, right? We are having the logic for the email notification, for the SMS notification. Further, if we want to create the WhatsApp notification, we can simply add the class. That is what we are doing, extending. We are extending the functionality, we are not modifying. Okay, so this is what OCP principle, that is open to extension and close to modification, right? Now here, to support WhatsApp, just create a new WhatsApp class, no changes to the existing code. Okay, so this was the OCP principle, that is open to extend, close to modification. And where we can apply this, where the requirement frequently changes, right? That means there is modification going on, right? So use polymorphism and abstract classes or interface. Got it? What is the benefits? Encourage extensible, that means we can extend, and modular design. minimize the regression bugs, because we are just extending it, so it will reduce the bugs, regression bugs, because we are not touching the previous code, right? So support plug and play modules. These are some related design patterns: strategy, decorator and factory. We will cover them in the upcoming sessions. So the third one is Liskov substitution principle. The definition is: object of a superclass should be replaceable with the object of its subclass without breaking the program. Okay, so I'm saying if we are using parent object, at that place we can use child object, right? So this is the principle, that is LSP, Liskov substitution principle. So the next line is: subclasses must honor the contract of the parent class. What does that mean? We will check in the example. Let's check this real world. If a program uses a bird is there, right? It should not work with the sparrow or parrot. Sorry, it should work with the sparrow or parrot because they can fly, but not with the penguin if can't fly, right? So if we are using this bird object in the, let's say in the functionality where they can fly, we are using this bird for the fly functionality, okay, in some code. Now we can use the object of its child, that is sparrow, right? Sparrow can fly. And what else? Parrot can fly, right? We can use the object of these child because they can fly, they are having the functionality to fly, okay. And this penguin should not work. Why? Because it can't fly. It is not having the functionality to fly. Now again, this is the child of bird, but we can't use it here, right? In this functionality, in this main method, we can say, alright. So let's take the code. We are having the bird class and we are having the method fly, right? So it's saying flying. After that we are having class ostrich, that is extending the bird, but ostrich can't fly, right? So we can't use this object also, right? So it says throw new exception, that is unsupported operation exception, right? So in the main function, if I am using the object of this ostrich, that will be the exception, right? So this is not the right way to write the code, right? So we are violating this LSP. Now let's see the code where we are applying this LSP. Okay, this is the violation. Let's see how we can achieve LSP. We are having this bird, right? Bird is there. After that we are having different class, that is after bird we are having one more class, that is flying birds. Okay, flying birds, that is extending what? Extending this bird, extends bird, right? So now I will say these birds can fly, right? These birds can fly. So this parrot, sparrow will be extending this flying bird. Okay, extend flying birds, because these are having the functionality of this flying, right? Flying. And for this ostrich, what we can say? Ostrich will extend simple bird, right? Got it? This is how we will achieve the LSP. Now in the main function, if I am using the object of this flying bird, let's say flying bird equal to new flying bird, right? Basically I need a bird which can fly, Got it? This is this object I am using in the main class. Now if I want to use this LSP principle, what does it say? It says we can replace the object of this parent with the child. What are the childs here? The parrot and the sparrow. That is extending the flying birds, means they can also fly. Alright, so I will be replacing this flying bird either with the parrot or the sparrow. Now this ostrich is not in the image, right? Ostrich is extending simple birds, that is this one, that is not having the functionality of fly. We are having functionality of fly in the further subclass. Okay, so here also you can see we are making next what we are making. We are making the class sparrow that is extending the flying birds. That means this is also having the functionality to fly. Ostrich is extending the bird. That means fly functionality will not be there. Okay, will not be there. Now ostrich does not need to override fly. Okay, so in the main function this will be happening. This is how we are achieving LSP, Liskov substitution principle. That means child class object can be replaceable with the parent class, right? So where we can apply this? So while overriding the methods, we should be careful, right? So if the class is having the functionality, then only we can override. We should override. This was the example here, right? If ostrich is not having the functionality to fly, we should not extend that class, right? So avoid violating superclass behavior or the contract. Same, the fly method, right? And benefits: predictable and the safe polymorphism, promotes correct inheritance, right? And these are the related design patterns. Composite template method. So basically what we need to do, we need to, like, if we are extending the class, parent class, we should check if the class having the method as parent, right? Having the functionality as parent. Here ostrich is not having the functionality to fly, so it should not extend this bird class, right? Because it is having the functionality to fly. So that's what is the Liskov substitution principle. The object of the super class should be replaceable with the object of subclass, means they should have the same functionality. Okay, the fourth one is interface segregation principle, ISP. What is the definition? Clients should not be forced to depend on the interface they don't use, right? So we should prefer the specific interfaces over one big general interface. Let's say we are having one interface. What we can have? Let's say we are having one interface, restaurant, in which we are having the non-veg food also, non-veg, and the veg food also, right? Let's say one person is there, veg person is there. So that is going to this restaurant. Okay, restaurant. Now he will be provided with both non-veg and the veg, right? This is guaranteed for this class to use to eat both of the veg and non-veg, right? Basically, what is the use case of this interface? If we are making any interface, we are providing the abstract classes, right? In the class which is implementing this, we should provide the definition for both the methods, right? Correct? So it should provide the definition for both the non-veg as well as veg. But I am saying this veg person will only eat the veg. That means the veg method. It will implement the veg method only. So here this is violating the ISP, right? So void for veg, it can provide the definition. Okay, it can eat the veg, but for non-veg, void non-veg, it will throw the exception. Okay, throw exception. Okay, so here comes exception. So this is violating the ISP principle. What is the definition of this? Client should not be forced to depend on the interface they don't use, right? So it is not using the non-veg, so it should not directly implementing this restaurant interface. Let's take one more example of the worker and the robot. Let's say we are having one interface worker that will work, that will eat, right? Now robot is there which is implementing the worker. Now robot will not eat, right? Will not eat. So it will throw the exception because we need to provide the definition for both of the abstract functions, abstract methods, right? But here our robot will not eat, so it will throw the exception for this method, right? So here's the line, robot doesn't eat, yet it is forced to implement eat. Okay, now how we can apply this ISP principle? Let's see the example. We are having the interface workable. Now we are having this interface, right? Worker, and we are having two definitions here, that is void work, void eat, right? But we should have different, right? For workable it will be different, for eat it should be different, so that robot can only implement the interface with the work functionality, right? How we can do? We can make an interface of this workable, so that our robot can directly implement this interface, right? So we are making the interface workable that will only work. Now there will be one interface that will only eat, right? So in the human class, human can also eat, can also work, right? So it will implement both of the interfaces, implements workable, eatable, and we will provide the implementation for both of the abstract methods, right? This is the implementation of human class. For the robot, it will only implement the workable interface that will only work, not eat. Got it? This is how we are achieving ISP. So this was the ISP principle. Okay, now every class implement only what is needed. Where to apply? Large interfaces with many unrelated methods, as we seen here, right? We are having the large interface with both work and the eat functionality. Now we can divide it into the smaller interfaces, smaller functionality. Prefer interface composition. What is the benefit? Benefit will be better separation of the concerns. Okay, we will be having different functionality, divided functionality, more flexibility, and fewer side effect, easier testing and mocking. So benefits will be common to all of the principles, right? And these are the design patterns, related design patterns. Now the fifth one is dependency inversion principle, DIP. Okay, what is the definition? Depends on the abstraction, not the concretions. Okay, so the high level modules should not depend on the low level modules. Okay, both should depend on the abstractions. Okay, let's see these terms. What is high level module? Your core business logic. Okay, low level utilities like database, APIs or logos, right? So this high level business logic should not depend on the low level modules. This will be like confusing for you. We will see the example after that. You will get. Basically, I'm saying there should be loose coupling. Okay, these are the points for the loose coupling only. This is the point for the loose coupling only. Tight coupling should not be there. Coupling should not be there. Okay, so abstraction, interfaces, and the abstract class. Okay, so what is DI? Dependency injection. What is dependency injection? Is the act of injecting required object or dependencies, right? Dependency injection is the act of injecting the required dependencies or the objects from the outside rather than creating them inside the class. Okay, this is what loose coupling, right? Loose coupling. We are doing what? We are creating a dependency outside the class and injecting them as the dependency. Okay, so what are the types of dependency injection? First one is constructor. We have seen this in the previous lectures, right? Pass the dependency via constructor. So whenever we call the object, we make the object, it will automatically call the constructor, right? In that constructor we can pass the dependency, let's say object of some different class. Second one is setter. We can inject the dependency via setter method, right? Let's say we are having one int age. So in the method, that is void set age, we can pass the dependency, required dependency here, right? This is what setter method for the age. Third one is field injection. Inject dependency into the field common in the Spring. This is basically the Spring part. Okay, so what is the real world example? We will see this constructor injection in the further code, right? So let's take the real world example. You use a charger with a standard socket. It doesn't matter who manufactures it as long as it fits the interface. Let's take the code example. Here we are violating the DIP, dependency injection, right? What we are doing? We are having the class MySQL database. Okay, MySQL database is there, which is having the method save, and it is saving the data string data, right? Now here I am using what? I am creating the object of this database, right? Here only in the user service class I am creating inside the class, right? And what else I am doing? Then I am calling the db.save inside this not constructor, save user method, right? So I am creating the dependency here inside the user service only. This is what tight coupling. User service is tightly coupled to the MySQL database. This is not the loose coupled. Great. So what is the example of DIP? How we can apply DIP, dependency injection? See what we can have. We can have the interface of database, right? Let's say database is there, which is having the method save, right? After that we are having one more class, that is MySQL database, which is implementing the database interface. We will provide the logic for that, right? Now in the class, that is user service, what we are having? We are creating the reference, not the object, just reference, right? Reference of DB, right? Of this DB interface DB. After that, what we are doing? In the constructor, see, this is what? Constructor injection. This is the type of DI, dependency injection, right? So we are using constructor injection. We are passing the dependency in the constructor here, right? And we are doing this dot db equal to db. That means we are allocating the object here, correct? So that is how we will use the constructor injection. What we are doing here, we are creating the object, of db outside the class, maybe in the in the main, right? In the main function, what we are having? Let's write it. Main function, what we can have? We will create this database. Okay, database db equal to new. Now we will be using this class method. Okay, MySQL database, right? So we are creating the object of this MySQL database. After that, we are creating the object of this user service. User service, user equal to new user service, and we are passing this db, right? So in the middle it can have this data also. Let's say it can have in the this method also, or we can pass as the constructor injection. Okay, constructor injection, the logic we can provide. Got it? So what is happening here? We are providing the dependency as constructor. Okay, as constructor, in the constructor, basically in constructor. This is called constructor injection. This is loosely coupled. Now user service works with any database that implements the database. Here we are using MySQL. In the future we can have other database also. Let's say MongoDB. Okay, MongoDB, right? We can use the object of this MongoDB and pass it as the parameter in the constructor. So what is happening here? See here, we are creating what? We are creating the object of this MySQL database in the user service, right? Let's say in the future if we are having some other database, okay, let's say MongoDB, then we need to modify the database class also and the user service class also. That means they are dependent, right? So this is what tightly coupled. Now here what we are doing, we are using the interface, right? That is having the save. Now in the future if I want to have extra class, extra database, let's say MongoDB, we can simply create a class of this MongoDB, right? Using this interface, let's say create class created. After that, in the main function only, I will make the object of this MongoDB and pass it in the object of this user service. So we are not changing anything in the user service. That means they are not dependent. These are loosely coupled. And for achieving loosely coupled, DI helped us, right? This constructor injection helped us. Dependency injection is this constructor injection, right? Constructor injection is the type of dependency injection, and that is what dependency injection principle. And where we can apply, anytime you use new inside a class, right? We are creating any object inside the class, where there we can apply the dependency injection. Use constructor injection, right? With the interfaces as we seen above this example. Benefits: loose coupling, highly testable, easier to swap implementations, right? So these are the main features, benefits of the DIP: loose coupling, highly testable, right? And these are the related design pattern: dependency injection, inversion of control, factory pattern. Now this is the summary table which we have covered today. So you can check this in the notes. Notes are available in the description.